Hello everyone, this is Professor He. Nice to see you again. The topic of this task is an introduction to fuel cell. Fuels like methane are commonly burned to provide thermal energy at high temperatures for use in heat engines. The reversible works obtained from the second law analysis of isothermal combustion and adiabatic combustion of methane reveal that the exergy of the reactants decreases by 288 megajoule per kilomole as a result of the irreversible adiabatic combustion process, along with 50% excess air and 25 degrees centigrade and 1 atm. The exergy of the hot combustion gases at the end of the adiabatic combustion process is 530 megajoule per kilomole methane. In other words, the work potential of the hot combustion gases is about 65% of the work potential of the reactants. It seems that when methane is burned, 35% of the work potential is lost before we even start using the thermal energy. The second law of thermodynamics suggests that there should be a better way of converting the chemical energy to work. The better way is, of course, the less irreversible way, the best being the reversible case. In chemical reactions, the irreversibility is due to uncontrolled electron exchange between the reacting components. The electron exchange can be controlled by replacing the combustion chamber with electrolytic cells, like car batteries. In the electrolytic cells, the electrons are exchanged through conductor wires connected to a load, and the chemical energy is directly converted to electric energy. The energy conversion devices that work on this principle are called fuel cells. That is, a fuel cell is an electrochemical device in which fuel and an oxidizer undergo a chemical reaction, providing electrical current to an external circuit and producing products. Fuel cells are not heat engines, and thus their efficiencies are not limited by the Carnot efficiency. They convert chemical energy to electric energy essentially in an isothermal manner. A fuel cell functions like a battery, except that it produces its own electricity by combining a fuel with oxygen in a cell electrochemically without combustion, and discards the waste heat. A fuel cell consists of two electrodes separated by an electrolyte such as a solid oxide, phosphoric oxide, or molten carbonate. The electric power generated by a single fuel cell is usually too small to be of any practical use. Therefore, fuel cells are usually stacked in practical applications. This modularity gives the fuel cells considerable flexibility in applications. The same design can be used to generate a small amount of power for a remote switching station, or a large amount of power to supply electricity to an entire town. Therefore, fuel cells are termed the microchip of the energy industry. The operation of a hydrogen-oxygen fuel cell is illustrated in the figure. Hydrogen is ionized in the surface of the anode, and hydrogen ions flow through the electrolyte to the cathode. There is a potential difference between the anode and the cathode, and free electrons flow from the anode to the cathode through an external circuit. Hydrogen ions combine with oxygen, and the free electrons enter the surface of the cathode, forming water. Therefore, the fuel cell operates like an electrolysis system working in reverse. In steady operation, hydrogen and oxygen continuously enter the fuel cell as reactants, and water leaves as a product. Therefore, the exhaust of the fuel cell is drinkable quality water. The fuel cell was invented by William Groves in 1839, but it did not receive serious attention until the 1960s, when fuel cells were used to produce electricity and water for the Gemini and Apollo spacecraft. Today, they are used for the same purpose in the space shuttle missions. Despite the irreversible effects such as internal resistance to electron flow, fuel cells have a great potential for much higher conversion efficiencies. At present, fuel cells are available commercially, but they are competitive only in some niche markets because of their high cost. Fuel cells produce high-quality electric power efficiently and quietly while generating low emissions using a variety of fuels such as hydrogen, natural gas, propane, and biogas. Recently, many fuel cells have been installed to generate electricity. Hybrid power systems that combine high-temperature fuel cells and gas turbines have the potential for very high efficiency in converting natural gas to electricity. Also, some car manufacturers are planning to introduce cars powered by fuel cell engines, thus nearly doubling the efficiency from about 30% for the gasoline engines to up to 60% for fuel cells. Intense research and development programs by major car manufacturers are underway to make fuel cell cars economical and commercially available in the near future. A fuel cell is an electrochemical device in which fuel and an oxidizer undergo a chemical reaction, providing electrical current to an external circuit and producing products. The fuel and oxidizer react catalytically in stages on separate electrodes, the anode and the cathode. An electrolyte separating the two electrodes allows passage of ions formed by reaction. Depending on the type of fuel cell, the ions may be positively or negatively charged. Individual fuel cells are connected in parallel or series to form fuel cell stacks to provide the desired level of power output. With today's technology, the preferred fuel for oxidation at the fuel cell anode is hydrogen because of its exceptional ability to produce electrons when suitable catalytes are used, while producing no harmful emissions from the fuel cell itself. Depending on the type of fuel cell, methanol and carbon monoxide can be oxidized at the anode in some applications, but often with performance penalties. Since hydrogen is not naturally occurring, it must be produced. Production methods include electrolysis of water and chemically reforming hydrogen-bearing fuels, predominantly hydrocarbons. Okay, that's all for this task. Thank you very much, and see you next time.